In the first images from the James Webb Space Telescope, astronomers stumbled upon faint red smudges, tiny, glowing specks scattered like dust in a cosmic attic. These aren't just distant stars, they're ancient galaxies, some 13.5 billion light-years away. They're light forged in the universe's infancy. But here's the twist: these red dots aren't static relics. They're actively birthing stars at rates 10 times faster than our Milky Way, their cores collapsing under gravity to ignite new solar systems. Yet, something strange is happening. Some of these galaxies are flickering, their light dimming and brightening in rhythms that defy current models. Could they be evolving in real time, or are we witnessing a cosmic dance of star formation and death? The JWST's unprecedented clarity has turned these dots into puzzles, each one a potential clue to how galaxies like ours might have once burned bright and how they might yet transform again. In the vast expanse of the universe, where light from distant galaxies takes billions of years to reach us, the James Webb Space Telescope has uncovered a phenomenon that has captivated scientists and stargazers alike: tiny red dots that hint at the universe's earliest epochs. These dots, first spotted in Webb's infrared images, are not mere cosmic specks but potential glimpses into the birth of galaxies, their evolution, and the secrets of how the universe grew from darkness into the luminous cosmos we see today. But what exactly are these red dots, and why are they so significant? Let's unravel this mystery step by step. The James Webb Space Telescope, launched in 2021, is designed to peer into the infrared spectrum, allowing it to detect light that has traveled immense distances across the universe. When astronomers first analyzed its data, they noticed faint, red-hued objects scattered across deep space images. These objects, initially dubbed little red dots, were unlike anything seen before. Their red color is not a trick of the telescope's optics but a result of the universe's expansion, a phenomenon known as redshift. As the universe expands, the light from distant galaxies stretches toward the red end of the spectrum, making them appear redder the farther away they are. These dots, therefore, are likely among the most distant galaxies ever observed, their light having journeyed for billions of years to reach us. But what makes these dots particularly intriguing is their brightness. While they are faint compared to nearby galaxies, their presence suggests they are massive, luminous structures forming in the early universe. The James Webb Telescope's infrared capabilities are key here. Because light from these distant galaxies has been stretched into the infrared range, Webb's instruments can capture it, revealing details that previous telescopes, like the Hubble Space Telescope, could not. This has allowed scientists to study these objects in unprecedented detail, offering a window into the universe's infancy. The significance of these red dots lies in their potential to shed light on the formation and evolution of galaxies. Galaxies, as we know them today, are vast collections of stars, gas, and dark matter. But in the early universe, these structures were smaller, denser, and still in the process of forming. The red dots may represent the first stages of galaxy assembly, baby galaxies that are still gathering mass and fueling their growth. By studying these objects, scientists can trace how galaxies evolved from their nascent forms into the sprawling systems we see today. This is crucial for understanding the timeline of cosmic history, from the Big Bang to the present day. One of the most surprising aspects of these red dots is their brightness. While they are faint compared to nearby galaxies, their luminosity suggests they are actively forming stars at an extraordinary rate. This is a key indicator of their evolutionary stage. In the early universe, galaxies were often more active in star formation due to the abundance of gas and the intense gravitational interactions between them. The red dots may be examples of these starburst galaxies, where massive numbers of stars are being born in a short period. Such galaxies are rare in the modern universe but were more common in the past, making them valuable targets for study. But how do scientists know these red dots are galaxies rather than other cosmic phenomena? The answer lies in the data collected by the James Webb Telescope. By analyzing the light from these objects, astronomers can determine their composition, temperature, and distance. For instance, the redshift of their light provides a direct measure of how far away they are. The more redshifted the light, the farther the galaxy. This has allowed researchers to estimate that these objects are among the earliest galaxies ever observed, forming just a few 100 million years after the Big Bang. This places them in a critical period of cosmic history when the universe was still young and the first galaxies were beginning to take shape. Another piece of the puzzle comes from the structure of these galaxies.
While they appear as small, red dots in images, their internal structure may be more complex.
Some studies suggest that these objects could be massive, clumpy galaxies with multiple components, rather than single, compact systems. This complexity hints at the dynamic processes at play in the early universe, where galaxies were still in the process of merging and interacting.
These interactions would have influenced their growth, shaping their morphology and influencing their star formation rates.
The discovery of these red dots also has broader implications for our understanding of the universe's expansion and the role of dark matter. Dark matter, which makes up the majority of the universe's mass, plays a crucial role in galaxy formation by providing the gravitational scaffolding that allows gas to collapse into stars and galaxies.
The presence of these distant galaxies suggests that dark matter was already in place in the early universe, facilitating the formation of these structures. By studying their distribution and properties, scientists can refine models of dark matter and its influence on cosmic evolution.
However, the story of these red dots is not without challenges.
One of the primary difficulties in studying these distant galaxies is their faintness.
Even with Webb's advanced instruments, detecting and analyzing their light requires sophisticated techniques and long exposure times. Additionally, the light from these galaxies is so faint that it can be easily overwhelmed by other sources of background noise, making it difficult to distinguish them from other cosmic objects. This has led scientists to develop new methods of data analysis, including machine learning algorithms, to sift through vast amounts of data and identify these elusive objects. Despite these challenges, the potential insights gained from studying these red dots are immense. They offer a unique opportunity to observe the universe as it was in its infancy, providing a direct look at the processes that shaped the cosmos.
By understanding how these early galaxies formed and evolved, scientists can better predict the future of the universe and the fate of galaxies like our own.
Moreover, these observations may help resolve long-standing questions about the distribution of dark matter, the rate of star formation in the early universe, and the mechanisms that drive galaxy evolution. The James Webb Space Telescope's ability to capture these red dots is a testament to the power of modern astronomy and the ingenuity of scientists who designed it. By pushing the boundaries of what is possible in space observation, Webb has opened a new era of discovery. As researchers continue to analyze its data, they are uncovering not just the existence of these distant galaxies but also the intricate web of processes that have shaped the universe over billions of years. Each red, therefore, is more than a mere speck of light. It is a beacon from the past, illuminating the path of cosmic evolution and inviting us to explore the mysteries of the universe. In the end, the story of these little red dots is a reminder of how much remains to be discovered about the universe. They challenge our understanding of galaxy formation, test the limits of our observational capabilities, and inspire new questions about the origins of the cosmos. As we continue to study these objects, we are not just looking at distant galaxies, we are peering into the very fabric of time itself, tracing the universe's journey from its earliest moments to the present day. And in doing so, we come closer to answering one of the most profound questions in science: how did the universe come to be? The James Webb Space Telescope, launched in December 2021 and beginning its science operations in July 2022, has already transformed our view of the cosmos. Among its many revelations, one particular discovery has captured the imagination of scientists and the public alike: a series of faint, red-brightened points of light, often referred to as little red dots, scattered across the images of distant star-forming regions. These objects, initially puzzling in their appearance, have become a focal point for understanding the early stages of star formation and the evolution of young stellar systems. But how did scientists uncover these enigmatic features, and what methods allowed them to confirm their nature? The journey to unravel this mystery is a testament to the power of modern astronomy and the sophistication of the instruments that now peer into the universe's deepest recesses. The first step in this discovery was the deployment of the James Webb Space Telescope itself. Designed to operate in the infrared spectrum, JWST's instruments are uniquely suited to capturing light from the earliest stars and galaxies, which are often obscured by cosmic dust. Its primary mirror, an impressive 6.5-meter diameter, collects and focuses light from these distant objects, while its advanced sensors convert that light into detailed images and spectra. The telescope's location at the second Lagrange point, about 1.5 million kilometers from Earth, ensures it remains in a stable, cold environment, minimizing thermal noise that could distort its observations.
This combination of engineering and location has allowed JWST to achieve unprecedented sensitivity, enabling it to detect faint objects that previous telescopes, like the Hubble Space Telescope, could not. The initial images released by JWST in July 2022 revealed a wealth of new cosmic phenomena, but it was during subsequent data analysis that the red dots began to emerge as a distinct pattern. These objects, appearing as small, red brightened points in deep space images, were initially identified through careful inspection of the telescope's high-resolution infrared data. The red color is a key indicator, as it suggests the presence of warm dust or gas heated by young stars. However, their faintness and the fact that they appeared in regions of active star formation hinted at a more complex story. Scientists knew that these dots could not be ordinary stars, as their brightness and color did not align with the expected properties of mature stars. Instead, they suspected these might be protostars, nascent stars still in the early stages of formation, surrounded by dense clouds of gas and dust. To confirm this hypothesis, researchers turned to JWST's suite of instruments, particularly the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI. These instruments operate in different wavelength ranges, allowing scientists to gather complementary data. NIRCam, which captures light in the near-infrared spectrum, is particularly effective at detecting the faint glow of young stars and the surrounding material. MIRI, on the other hand, operates in the mid-infrared range, where the thermal emission from dust and gas becomes more prominent. By combining data from both instruments, scientists could build a more complete picture of these objects. For example, NIRCam's images revealed the positions and brightness of the red dots, while MIRI's data provided insights into the temperature and composition of the surrounding material. The process of confirming these objects as protostars involved a multi-step approach. First, scientists compared the newly detected red dots with existing astronomical catalogs and previous observations from other telescopes, such as the Hubble Space Telescope and the Spitzer Space Telescope. These comparisons helped determine whether the dots were new discoveries or had been previously missed due to the limitations of earlier instruments. For instance, some of the red dots were found in regions of star formation that had been studied before, but their faintness meant they had not been detected in previous surveys. This highlighted the importance of JWST's enhanced sensitivity and resolution in uncovering such objects. Next, researchers used spectroscopy to analyze the light emitted by these objects. Spectroscopy involves breaking down the light into its component wavelengths, which can reveal information about the temperature, composition, and motion of the source. JWST's near-infrared spectrograph, NIRSpec, and mid-infrared spectrometer, MIRI's spectroscopic mode, were critical in this process. By examining the spectral signatures of the red dots, scientists could identify specific molecular lines that indicate the presence of warm dust or gas. For example, the detection of certain molecular species, such as carbon monoxide or water vapor, suggested that these objects were indeed young stars surrounded by protoplanetary disks. These findings provided strong evidence that the red dots were not just distant stars but active sites of star formation. Another crucial aspect of the confirmation process was the use of follow-up observations and modeling. Scientists employ computational models to simulate the expected properties of protostars and compare them with the observed data. These models took into account factors such as the mass of the protostar, the density of the surrounding material, and the effects of radiation from nearby stars. By adjusting these parameters, researchers could refine their understanding of the object's physical characteristics. For example, some of the red dots were found to be part of larger clusters of young stars, suggesting that they were forming in a dense environment where multiple stars could be born simultaneously. This clustering effect is a common feature in star-forming regions and provides further support for the protostar hypothesis. The timeline of this discovery is as remarkable as the findings themselves. The initial detection of the red dots occurred within months of JWST's science operations, during the first wave of data release in 2022. However, the confirmation process took several months of analysis and collaboration. Scientists worked tirelessly to process the vast amounts of data generated by JWST, using advanced algorithms and machine learning techniques to identify patterns and anomalies. This data processing was essential, as the sheer volume of information required careful calibration and filtering to ensure accuracy. The collaborative nature of this work was evident in the way researchers from different institutions and countries shared insights and resources,
pooling their expertise to tackle the challenges of interpreting the data. One of the most intriguing aspects of the red dots is their potential to shed light on the evolution of stars and planetary systems. By studying these objects, scientists can gain insights into the earliest stages of star formation, a process that is still not fully understood. For instance, the presence of protoplanetary disks around some of the red dots suggests that planets may be forming alongside these young stars. This connection to planetary system formation makes the red dots not just fascinating in their own right but also crucial for understanding the broader context of stellar and planetary evolution. The implications of these findings extend beyond the immediate study of the red dots. They highlight the importance of infrared astronomy in exploring the universe's hidden corners. Many of the most active star-forming regions are shrouded in dust, which blocks visible light but allows infrared radiation to pass through. JWST's ability to observe in the infrared spectrum has therefore opened up new avenues of research, revealing phenomena that were previously inaccessible. The red dots are a prime example of how this capability has led to groundbreaking discoveries, offering a glimpse into the dynamic processes that shape the cosmos. As the research on the red dots continues, scientists are also exploring the possibility that these objects may represent different stages of evolution. Some may be in the earliest phases of star formation, while others could be more mature protostars or even young stars transitioning into the main sequence. This variability adds another layer of complexity to the study, as researchers seek to determine the exact evolutionary paths of these objects. The ability to observe such a wide range of stages in a single region of space is a rare and valuable opportunity, providing a comprehensive view of star formation processes. In conclusion, the discovery and confirmation of the James Webb Space Telescope's little red dots represent a significant milestone in astronomical research. Through the combined efforts of advanced instrumentation, meticulous data analysis, and collaborative science, researchers have begun to unravel the mysteries of these enigmatic objects. The journey from initial detection to confirmation has demonstrated the power of modern astronomy and the potential for future discoveries. As the study of these red dots progresses, they will undoubtedly continue to offer new insights into the origins of stars and the evolution of the universe, reminding us of the vast, intricate processes that shape the cosmos. Inside the mystery of the James Webb Space Telescope's little red dots and how they might be evolving, this part of our deep dive into Inside the Mystery of the James Webb Space Telescope's little red dots and how they might be evolving focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have gazed at the cosmos, peering into the vast distances of space to unravel the universe's secrets. But until the James Webb Space Telescope, JWST, launched in 2021, our view of the early universe remained limited by the constraints of technology and the very nature of light itself. The red dots now capturing our attention in JWST's images are not just distant galaxies or star-forming regions, they are echoes of a time when the universe was young, still shaping itself, and teeming with possibilities. To understand how we arrived at this moment, we must look back to the milestones that laid the foundation for today's discoveries. The journey began in the early 20th century, when scientists first began to grasp the scale of the universe and the challenges of observing it. Edwin Hubble's groundbreaking work in the 1920s and 1930s revealed that the universe was not static but expanding, a revelation that reshaped our understanding of space and time. Yet, even with Hubble's insights, the tools to study the universe's infancy were still rudimentary. Ground-based telescopes, while powerful, were hampered by Earth's atmosphere, which distorted light and limited the clarity of observations. The idea of a space-based telescope emerged as a solution, a vision that would take decades to materialize. In the 1960s and 1970s, scientists and engineers began designing the first space telescopes, driven by the desire to overcome atmospheric interference and capture clearer, more detailed images of the cosmos. The Hubble Space Telescope, launched in 1990, became a landmark achievement. It was the first major telescope to operate in space, offering unprecedented views of distant galaxies, nebulae, and celestial phenomena. Hubble's images of the universe's distant past, like the iconic cosmic snake or the Hubble Deep Field, revealed galaxies that were billions of light-years away, giving us a glimpse into the early universe. However, Hubble's capabilities had their limits. Its optical and ultraviolet sensors could detect light from objects up to about 13 billion light-years away, but they struggled to peer further back in time. The universe's expansion had stretched the light from the earliest galaxies into longer wavelengths, beyond the range of Hubble's instruments. This is where the James Webb Space Telescope's design comes into focus. JWST was conceived not just as an upgrade to Hubble, but as a revolutionary leap in technology, capable of observing the universe in the infrared spectrum. Infrared light, which is invisible to the human eye, carries the signatures of the earliest stars and galaxies, those formed just a few 100 million years after the Big Bang. To capture this light, JWST's mirror is nearly 3 times larger than Hubble's, allowing it to gather more light and resolve finer details. But size alone wasn't enough. JWST's instruments are cooled to near absolute zero, ensuring that the telescope's own heat doesn't drown out the faint signals from distant objects. This cryogenic cooling is critical, as even the faintest infrared light from the early universe is incredibly weak, requiring extreme sensitivity to detect. The design of JWST was decades in the making, rooted in the lessons of earlier missions and the growing understanding of the universe's evolution. Before Hubble, astronomers relied on ground-based telescopes, which, despite their power, were limited by atmospheric distortion. The development of adaptive optics, a technology that uses computer-controlled mirrors to correct for atmospheric turbulence, helped mitigate some of these challenges, but it couldn't fully eliminate them. Space-based telescopes, like Hubble, offered a solution by placing instruments above Earth's atmosphere, where they could capture clearer, more consistent images. Yet, even Hubble's achievements were constrained by its technology. The infrared capabilities of JWST were a direct response to the limitations of earlier missions. Scientists had long theorized that the earliest galaxies would be faint, distant, and shrouded in dust, making them difficult to observe. But with JWST's infrared sensors, these objects are now coming into focus, revealing details that were previously impossible to discern. The historical context of these advancements is essential to understanding the significance of JWST's findings. The study of distant galaxies has evolved from speculative theories to precise observations, driven by technological breakthroughs and the accumulation of data from earlier missions. In the 1980s and 1990s, astronomers used Hubble to map the distribution of galaxies across the universe, leading to the discovery that the universe's expansion was accelerating due to dark energy. These findings, while groundbreaking, still left many questions unanswered. How did the first galaxies form? What role did dark matter play in their evolution? And what were the conditions in the universe's earliest moments? JWST was designed to address these questions by providing a deeper, more detailed view of the cosmos. Its ability to observe in the infrared spectrum allows it to detect light that has traveled for billions of years, offering a window into the universe's infancy. The red dots now visible in JWST's images are likely the remnants of these early galaxies, their light stretched and dimmed by the expansion of the universe. But how did we arrive at this point in our understanding? The answer lies in the cumulative efforts of generations of scientists, engineers, and visionaries who laid the groundwork for space-based astronomy. The first space telescopes, like the Soviet Union's Orbiting Astronomical Observatory, OAO, in the 1960s, were experimental, but they demonstrated the potential of observing the universe from space. The 1970s saw the conceptualization of the Hubble Space Telescope, with its design influenced by the need to overcome atmospheric limitations and study the universe in greater detail. When Hubble was launched, it faced initial challenges, including a flawed mirror that required a servicing mission to correct. Yet, its eventual success proved that space-based telescopes could revolutionize our understanding of the cosmos. The data collected by Hubble and other missions in the 1990s and 2000s laid the foundation for JWST's mission. By the early 2000s, astronomers had identified the existence of high-redshift galaxies, objects so far away that their light has been stretched into the infrared. These galaxies, which formed just a few 100 million years after the Big Bang, were thought to be the building blocks of the larger structures we see today. However, their exact properties and formation mechanisms remained unclear. JWST was designed to resolve these mysteries by providing higher resolution images and more detailed spectral data. The telescope's instruments, including the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, are optimized to capture the faintest infrared signals, enabling astronomers to study these distant objects in ways previously impossible. The historical context of these developments underscores the significance of JWST's findings. The red dots in its images are not just distant galaxies, they are the first light in the universe, the seeds of cosmic structures, and the remnants of a time when the universe was still young and dynamic. To fully appreciate their importance, we must recognize the long journey that brought us to this moment. The study of the early universe has evolved from theoretical models to observational science, driven by the relentless pursuit of knowledge and the advancement of technology. Each step in this journey has built upon the previous, culminating in the launch of JWST and its ability to peer into the cosmos with unprecedented clarity. As we look at these red dots, we are not just observing distant stars and galaxies, we are witnessing the universe's earliest moments, a testament to the power of human curiosity and the ingenuity of scientific exploration. In the vast expanse of the cosmos, where light travels for billions of years to reach our eyes, the James Webb Space Telescope has unveiled a phenomenon that has captivated scientists and stargazers alike. These tiny red dots, scattered across the images captured by the telescope, are not mere accidents of light but potential clues to some of the most profound mysteries of the universe. Yet, their exact nature remains an enigma, sparking debates and inspiring new questions about the origins and evolution of celestial objects. While the telescope's capabilities have allowed us to peer deeper into the universe than ever before, these red dots challenge our understanding of what lies beyond our current knowledge. They are not just distant stars or galaxies, they may represent something even more intriguing, perhaps the first glimpses of cosmic structures in their infancy, or perhaps something entirely unexpected. As scientists analyze the data, the mystery of these red dots continues to unfold, revealing the complexity of the universe and the enduring quest to unravel its secrets. What exactly are these dots? Are they remnants of ancient galaxies, or could they be the birthplaces of new stars? The answers may lie in the very fabric of the cosmos, waiting to be discovered. Yet, for now, the questions remain, and the search for answers continues. The James Webb Space Telescope has given us a powerful tool to explore these mysteries, but the journey to understand them is just beginning. Scientists are now working to decipher the nature of these red dots, and in doing so, they are uncovering new layers of complexity in the universe's history. The debate over their identity is far from settled, and each new observation brings both clarity and more questions. For instance, some researchers believe these dots could be distant galaxies in the early universe, their light stretched by the expansion of space into the red part of the spectrum. Others suggest they might be star-forming regions, where massive clouds of gas and dust are collapsing to create new stars. Still, there are those who wonder if these dots could represent something entirely different, a phenomenon that defies current scientific models. The uncertainty surrounding their nature is what makes them so fascinating. It is this ambiguity that drives scientific inquiry, pushing researchers to refine their theories and test new hypotheses. The James Webb Space Telescope's ability to capture such detailed images has opened a new window into the universe, but it has also revealed the limits of our current understanding. These red dots are a reminder that even with advanced technology, the cosmos still holds mysteries that challenge our knowledge. As scientists continue to analyze the data, they are not only seeking to identify these dots but also to understand their implications for the broader picture of cosmic evolution. The potential for these objects to be evolving is a particularly intriguing aspect of the mystery. If these dots are indeed young galaxies or star-forming regions, their appearance could indicate a dynamic process of growth and change. This raises the question of whether these objects are static or if they are in a state of transformation, shedding light on the life cycles of celestial bodies. The idea that these dots might be evolving adds another layer of complexity to the mystery, suggesting that the universe is not a static entity but a dynamic system in constant motion. However, the scientific community is still grappling with the implications of these findings. While some researchers are optimistic about the potential for these dots to reveal new insights, others remain cautious, emphasizing the need for further observation and analysis. The debate over their nature is not just about what these dots are but also about how they fit into the larger framework of astrophysical theory. For example, if these dots are indeed young galaxies, their existence could challenge existing models of galaxy formation, suggesting that the processes that shaped the universe in its early stages may be more complex than previously thought. On the other hand, if they are star-forming regions, their study could provide valuable information about the conditions under which stars are born, offering new perspectives on the life cycles of stars and their role in the universe. The potential for these dots to be evolving also raises questions about the timescales involved in their development. Are these objects in the early stages of their formation, or are they in a transitional phase? Understanding their evolutionary status could provide critical insights into the processes that govern the formation and evolution of celestial structures. However, the answers to these questions are not yet clear. The scientific community is still in the process of interpreting the data, and the debate over the nature of these red dots is far from over. This uncertainty is what makes the mystery so compelling. It is a testament to the enduring nature of scientific inquiry, where each new discovery opens up new avenues of exploration and raises new questions. The James Webb Space Telescope has provided a powerful tool for this exploration, but the journey to understand these dots is just beginning. As researchers continue to analyze the data, they are not only seeking to identify these objects but also to understand their significance in the broader context of the universe's history. The potential for these dots to be evolving adds another dimension to the mystery, suggesting that the universe is a dynamic and ever-changing entity. However, the scientific community must proceed with caution, recognizing that the answers to these questions may not be straightforward. The debate over the nature of these red dots is a reminder that even with advanced technology, the cosmos still holds mysteries that challenge our understanding. As scientists continue to explore these questions, they are not only uncovering new insights but also deepening our appreciation for the complexity of the universe. The mystery of these red dots is far from solved, but it is this very uncertainty that drives the pursuit of knowledge. It is a reminder that the universe is vast, intricate, and full of surprises, and that the quest to understand it is an ongoing journey. For now, the red dots remain a symbol of the mysteries that await discovery, a testament to the enduring curiosity that drives scientific exploration. As the James Webb Space Telescope continues to send back its data, the story of these red dots will undoubtedly evolve, revealing new layers of complexity and deepening our understanding of the cosmos. The mystery of these dots is not just about what they are but also about what they represent, a glimpse into the unknown, a challenge to our current knowledge, and a reminder of the infinite possibilities that lie beyond our current understanding. The answers may still be hidden in the depths of space, but the search for them continues, driven by the same curiosity that has propelled humanity to look up at the stars for millennia. As the James Webb Space Telescope continues to unveil the cosmos, the enigmatic red dots it captures are far from the end of the story. These faint, glowing specks, likely distant galaxies or star-forming regions, hold clues to the universe's evolution, but their full significance remains under investigation. What's next? A wave of upcoming missions, advanced instruments, and new observational techniques will soon shed light on these mysteries, potentially confirming, extending, or even challenging our current understanding. Let's explore how the scientific community is preparing to dive deeper into the secrets these red dots might hold. The first step in unraveling this mystery lies in the next generation of space-based observatories. Among them, the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will play a critical role. While not as powerful as Webb in resolving fine details, the Roman telescope will survey vast swaths of the sky with its wide field of view. Its primary mission is to map dark matter and study the distribution of galaxies across cosmic time, but its observations could also help contextualize the red dots. By tracking how these distant objects evolve over decades, Roman may reveal patterns in their brightness or structure that hint at their true nature. For instance, if the red dots are young galaxies undergoing intense star formation, Roman's data could help determine how frequently such galaxies appear in the universe's history, offering insights into the rate of star formation in the early cosmos. Meanwhile, the James Webb Space Telescope itself is already preparing for follow-up studies. While its initial images have captured these red dots as faint, diffuse features, Webb's capabilities extend far beyond what was possible with its predecessor, Hubble. With its infrared vision, Webb can peer through cosmic dust to observe regions where stars are born. Scientists are already planning targeted observations to study these dots in greater detail. For example, if a red dot is suspected to be a distant galaxy, Webb's spectroscopic instruments could analyze the light it emits to determine its composition, age, and distance. By measuring the redshift of the light, researchers can calculate how far away the galaxy is and how long its light has traveled to reach us. This could help determine whether these objects are indeed ancient galaxies or something entirely different, like a cluster of stars or a protogalaxy in the process of forming. But Webb's work is just one part of a broader effort. Ground-based telescopes are also stepping up to the challenge. The Extremely Large Telescope, ELT, currently under construction in Chile, will soon become the largest optical telescope in the world. With its massive 39-meter mirror, the ELT will have the power to resolve details that even Webb cannot. If the red dots are part of a larger structure, such as a group of galaxies or a massive star-forming region, the ELT could provide the high-resolution images needed to confirm their nature. Additionally, the ELT will be equipped with advanced spectrographs capable of analyzing the chemical composition of these objects, offering clues about their age, temperature, and the elements present in their atmospheres. These data could help distinguish between different possibilities, such as whether the red dots are young galaxies, star-forming clouds, or even rare cosmic phenomena like tidal dwarf galaxies or dark matter clumps. Another key player in this quest is the Euclid Space Telescope, set to launch in the early 2030s. Euclid's primary goal is to study dark energy and the large-scale structure of the universe, but its observations could also intersect with the mystery of the red dots. By mapping the distribution of galaxies and their light distortion caused by dark matter, Euclid may help identify regions where these red dots are concentrated. If the dots are linked to dark matter interactions, Euclid's data could reveal patterns that align with theoretical models. Moreover, Euclid's infrared invisible light capabilities will allow it to study how these objects evolve over time, providing a complementary perspective to Webb's observations. Together, these space telescopes could paint a more complete picture of the universe's history and the role these enigmatic features play in it. However, the search for answers may also require new technologies and techniques. One promising approach is the use of interferometry, a method that combines signals from multiple telescopes to achieve higher resolution. While interferometry has been used in radio astronomy for decades, recent advancements in optical and infrared interferometry could enable ground-based telescopes to study these red dots with unprecedented clarity. For example, projects like the Gravity Instrument at the Very Large Telescope, VLT, in Chile have already demonstrated the potential of interferometry to resolve distant objects. If applied to the red dots, this technique could reveal whether they are individual galaxies, clusters of stars, or something entirely new. Additionally, the development of next-generation adaptive optics technology that corrects atmospheric distortions in real time will further enhance the ability of ground-based telescopes to observe these faint features. The mystery of the red dots also raises broader questions about the universe's evolution. If these objects are indeed young galaxies or star-forming regions, their existence could challenge existing models of galaxy formation. Current theories suggest that galaxies formed in a hierarchical manner, with smaller structures merging to form larger ones over billions of years. However, if the red dots represent galaxies that formed earlier or under different conditions, this could indicate that our understanding of cosmic evolution is incomplete. For instance, if these dots are unusually bright or have unique properties, they might hint at alternative pathways for galaxy formation, such as the role of dark matter in triggering star formation or the influence of cosmic web structures on galaxy growth.
Resolving these questions could require not only new observations but also revisions to the theoretical frameworks that guide our understanding of the universe. In parallel, the study of these red dots may also shed light on the nature of dark matter itself. Dark matter, which makes up the majority of the universe's mass, does not interact with light, making it invisible to traditional telescopes. However, its gravitational influence can be detected through its effects on visible matter. If the red dots are associated with dark matter halos or structures, their distribution and behavior could provide indirect evidence of dark matter's properties. For example, if these objects are found in regions where dark matter is particularly dense, it could support theories about how dark matter clumps together. Conversely, if they are distributed in a way that contradicts existing models, it could prompt new hypotheses about the nature of dark matter. The upcoming missions and instruments mentioned earlier will play a crucial role in testing these ideas, offering a unique opportunity to probe one of the greatest mysteries in astrophysics. Beyond the technical and theoretical challenges, the study of these red dots also underscores the importance of continued exploration in space. The James Webb Space Telescope, the Nancy Grace Roman Space Telescope, the Extremely Large Telescope, and future missions like Euclid represent a collective effort to push the boundaries of human knowledge. Each of these instruments brings a unique perspective, and together they form a powerful network of tools capable of addressing complex questions about the universe. As scientists analyze the data from these missions, they may uncover not only the answers to the mystery of the red dots but also new questions that will drive the next wave of discoveries. The journey to understand these enigmatic features is far from over, and the path ahead is filled with possibilities. In the end, the red dots captured by the James Webb Space Telescope are more than just distant objects, they are windows into the past, revealing the universe's earliest epochs and the processes that shaped it. Whether they are young galaxies, star-forming regions, or something entirely new, their study will continue to inspire curiosity and drive innovation in astronomy. As we look to the future, the combination of advanced technology, international collaboration, and a relentless pursuit of knowledge will ensure that the mystery of these red dots remains an exciting frontier in the exploration of the cosmos. The universe has always had secrets to share, and with each new observation, we take another step closer to understanding its vast, intricate story. So what does all this mean for our understanding of the universe? Let me break it down. First, those little red dots aren't just random specks, they're likely the earliest stages of stars or protostars, still shrouded in gas and dust. JWST's infrared eyes have peered through the cosmic haze to reveal these hidden nurseries, where gravity is pulling together material to form new stars. Some of these dots might still be in their infancy, their cores barely ignited, while others could be on the cusp of becoming full-fledged stars. What's fascinating is that we're seeing these processes unfold in regions of the universe that are billions of light-years away, meaning we're witnessing events that happened when the cosmos was just a fraction of its current age. This gives us a rare glimpse into how stars, and the galaxies they power, began. But here's the twist, some of these dots might not even be stars at all. Astronomers are now considering the possibility that a few of them could be massive planets, or even systems of planets, still forming around their young host stars. If that's true, it would mean we're looking at the birth of entire planetary systems, right there in the depths of space. And this raises an even bigger question: how common are these processes across the universe? Are we seeing a rare phenomenon, or is this a standard part of galaxy evolution? The data from JWST is still being analyzed, but the implications are staggering. These dots could rewrite our understanding of how stars form, how galaxies grow, and even how life might emerge in other parts of the cosmos. But the journey isn't over. Every image from JWST adds another piece to this puzzle, and every new finding opens up more questions. For now, we're left with a sense of wonder and a lot of work ahead. If you follow this deep dive, you've seen how science thrives on curiosity, on asking what if and then finding ways to test those ideas. But this is just the beginning. The James Webb Space Telescope is still sending back data, and the mysteries it uncovers will keep us busy for years. So if you've enjoyed this episode, hit that subscribe button to join us for more daily explorations of the cosmos. And if you have your own theories or questions about these red dots, we want to hear from you. Drop a comment below, because the universe is full of mysteries, and every voice helps us uncover the next one.